Continuing our story of carbon cycle, the chapter 1, obviously the first one was 0, which was just an introduction. Chapter 1 is called Moods of the Carbon Cycle, where we will look at positive and negative feedbacks at different timescales, which is very unusual for the same process like carbon cycle to have a positive feedback as well as a negative feedback, but it always comes down to energy balance. As we are emitting more and more greenhouse gases, we are changing the energy budget of the Earth's greenhouse effect, and that's going to give us warming, which we want to avoid, right? If we go back to the solar system, we have Mercury, Venus, Earth, the third rock from the Sun, and Mars, and we all know that Venus has a very hot 460 degrees centigrade at the surface. We have a balmy 15 degrees centigrade as the global mean temperature, and Mars has minus 50 degrees centigrade. Obviously, the distribution or the energy received from the Sun dies off as 1 over r squared, which is the distance between the Sun and a particular planet you're looking at, and the closeness to the Sun partly explains the temperatures on Venus, but you also need a greenhouse effect that is able to trap so much more energy and create such very hot temperatures, whereas this has a minus 50 degrees centigrade temperature at the surface, which is a runaway cooling, and we have what is called often the Goldilocks syndrome. So we have neither too hot nor too cold, a perfect blanket that is often argued to be responsible for finding life on Earth, but now we know that there are potentially some sorts of lives possible on other planets in the solar system, as well as the moons of some of the planets which have water either frozen on the surface, water below the surface, frozen water below the surface, and so on and so forth. The temperatures we can look at in terms of the differences. So if we look at atmospheric pressure and compositions, and in terms of trace gases and so on, observed temperatures, and these are expected from the calculations. So you can see they are pretty close, but here Venus, what you would expect just from the distance from the moon and energy balance would be very different. You go from 232 to 735, whereas on Earth, if you didn't have any greenhouse effect like here, you would get 255, which is minus 18 degrees centigrade. You add the greenhouse gases, we go to 288 or 15 degrees centigrade, whereas here we go to 735. So obviously there is a runaway greenhouse effect here. This is Kelvin and degree centigrade, of course. Mars has got a tiny bit of a greenhouse effect, but you can see that it's still got a runaway cooling effect. Okay, so you have here pressure of the various trace gases. Carbon dioxide dominates, whereas on Earth we have nitrogen dominating. You have sulfur dioxide and argon as well. So we can see here nitrogen dominates, oxygen is the next one, argon, and then CO2 is a trace gas, and water vapor is called a feedback gas. So warmer the Earth gets, there will be more water vapor, and if Earth gets colder, let's say because of ice ages, then there will be less water vapor in the atmosphere, and so on. So energy balance, which typically is looked at like this, tends to heavily depend on this blanket of trace gases or greenhouse gases that can trap the outgoing long wave and allow some of the incoming short wave from the sun to get through. So we receive 341 watts per meter squared at the top of the atmosphere, and about 79 watts per meter squared are reflected by the clouds and the atmosphere including the dust and the water vapor and other processes. And the surface reflects about 23 watts per meter squared. So you have about a net albedo of the Earth, or the reflectivity, of 30% or 0.3. So we are losing 102 watts per meter squared straight off as a short wave. The rest of it is doing various things like heating the surface, evaporating water from the soil and lakes and rivers, and melting glaciers, and evaporation from the ocean, and so on. So all that together, there is got to be outgoing thermal energy or long wave radiation from the Earth to the space to keep equilibrium. But because of these greenhouse gases, we bounce around the energy. So the atmosphere does absorb some of the short wave, and the rest of it rest of the short wave makes it to the surface. And you can see that even though we are only receiving 341 watts per meter squared here, there are numbers here that are much larger, like 396 watts per meter squared here, and 333 watts per meter squared over here, and so on, because the long wave energy going from the surface is going to be absorbed by the atmosphere, the clouds, and so on. And that is going to emit long wave both towards space and back towards the Earth. So the main calculation that if you do formally you will find is that the most important effect of a greenhouse gas shield or blanket is that the surface temperature can get warmer than if you had no greenhouse gas blanket. Okay, so that's how you get more energy. It is really like putting on a blanket when it's cold. The blanket traps your own body heat and makes you feel warmer. Even if it's not an electric blanket, just a normal blanket is just going to trap your own body heat, which is what the greenhouse blanket of the Earth is doing. Okay, so that's a very short run through the energy balance. We will just run also through the photosynthesis, which is taking solar energy and combining carbon dioxide and water vapor, or water, to form molecules of carbohydrate or sugar and releasing oxygen. For each unit of carbohydrate or sugar that's stored away, that's not respired, we end up having an additional molecule of oxygen remaining because of photosynthesis. But usually respiration just burns the carbohydrate and the sugar, so uses oxygen in aerobic respiration to give us back carbon dioxide and water vapor. So glucose, so this unit of sugar ends up producing many complex molecules of glucose, a carbohydrate, and a sugar here. Proteins have reduced carbon sitting here at CH with amino group here and carboxyl group here and a side chain. So that's a building block of a protein. And life also needs fatty acids or lipids for structures, and the way various fuels are formed works on these basic molecules that are produced by biological activities and then buried away, and over time under pressure and temperature various things get formed, as we will see in the next podcast. Okay, so let me close this here as a brief introduction to energy balance, where again carbon dioxide, carbon cycle plays a critical role in the energy balance, which is why global warming and fossil fuel burning and carbon emissions because of land use change, cement, steel, and so on, agriculture are important, because energy balance is affected by the carbon cycle as well.